root of 2 times n times phi max times f equals to E RMS. Then the final expression of the induced voltage from time change in magnetic field equals to E RMS equal to 4.44. Of course, 2 pi over square root of 2 is 4.44 times n times phi max times f. So okay, there is a question. Since we use the current in the coil to create the flux and the coil is a conductor, so originally there is a voltage in the coil. How the possible? Okay, so if we use the current in the coil, to create flux, and the coil is a conductor, so originally there is a voltage in the coil. How it's possible that flux creates the voltage? Okay, okay, no problem. So here, of course, we have a flux. So the origin of this flux, we are going to induce a voltage or generate a voltage in the magnetic circuit using a flux. Of course, this flux has been generated using a current or using a magnet, for example. So this is another voltage. So we are not talking about the original voltage that we used to create the flux. Okay, do you get what I'm talking about? Okay, that's okay. So for example, in the transformer, look at the transformer. We have a voltage. Okay, I can repeat. So your colleague said why we generate voltage if we have an original voltage, because this flux has been generated using a voltage. Okay. Yes, as I said, why we induce or generate voltage, and we have already voltage. Of course, this is another voltage, not the voltage that's been used to generate flux. For example, the transformer, we are going to see it, inshallah, in the next chapter. We have the primary winding and we have the secondary winding. So if we want to generate a voltage in the secondary winding, we are using the flux that's being generated by the voltage of the primary winding. Also in electric machines, if we want to generate a current, for example, in the rotor, we are using the flux that has been generated with another voltage in the stator. So they are not the same. So this is the first case if we want to generate voltage using a time changing magnetic field. So I repeat again that this expression can be valuable only if we have an alternative, because if the phi is constant in case of DC voltage, so there is no voltage, there is no flux is constant, so this expression, the derivative of constant, is 0. That's why the transformer used only for AC voltage and AC currents. So the transformer cannot be used for DC voltage and DC currents. Okay, because of this expression. So I can ask you another time, inshallah, why we cannot use transformer in case of DC. Okay, it's because of this Faraday's law. Let's see another case. Firstly, the induced voltage from time change in magnetic field. The second case, we have an example before passing to the second case. So the example, a single phase 120 volt. We use this the same magnetic circuit. Okay, the magnetic circuit shown in the figure number 7. We use it for this example. So a single phase 120 volts power supply, 60 hertz, is connected to the coil as shown in the figure number 7. The coil has 200 turns. Okay, so the parameters of the core as follow. The length of the core, so which is the path of the flux, is 100 centimeter. The cross-section area is 20 centimeters square. The relative permeability of the core is 2500. Obtain the expression of the flux density in this core. So how we can, yes, it's RMS, yes. That voltage is RMS, okay. Okay, so let's go to the board to try to solve this example. So they said, the question said, obtain the flux density of the core. How we can obtain the flux density? So the flux density, or the flux density, of course. So we know that the flux density B equals to can be found using, for example, B equals to yes, it's in RMS, don't worry about this. Okay, it's in RMS. So as we said, the flux density B can be equals to mu times H, or it can be equals to also to phi over A. Okay, in this case we don't have H, and we want to find the flux density. So we can use the expression of the induced voltage. Okay, let's go back to the presentation. So we use the expression according to Faraday's law. The maximum flux can be found like this. So the maximum flux according to Faraday's law, the last expression we have seen, which said that E RMS, of course, it's the voltage, equals to 4.44 times F times N. So the expression you have seen, the last expression. So according to this expression, the maximum flux equals to V over 4.44 times F times N. And all of these are given. F is 60 and N is 200. So the maximum flux equals to 120 over 4.44 times 60 times 200, and it's equal to 0.002253. So this is the expression of the maximum flux. We are looking not for the flux, we are looking for the flux density. So the flux density B. So if we found the maximum flux B, also the density will be max. We will be maximum density. So the maximum field density B equals to phi over A, which is the cross section. Okay. Why V? It's in RMS. Okay, let's go back to the previous slide. Okay. So at the beginning, the voltage was maximum. Okay. From this expression, يعني جبنا الاكسبريشن تاع AC voltage V max cosine omega t. احنا لي we choose بدلنا برك درنا change of variable, for example E max بدلناها to square root of 2 تاع E RMS. Okay, it's our choice. And in our calculation we use RMS. يعني باش نقول لكم ممكن نتوما you have studied AC circuit before, but here in the electric machines generally we use only RMS. Okay, we don't care about the other peak to peak ومانيش عارف. Okay, we use mainly we use only the RMS values. That's why we have changed it E max to E RMS. Then the last expression is RMS, of course. Okay, so the voltage is RMS. Here V it's given in RMS. It's not a maximum. Okay, so V is an RMS. Okay, let's go back to the exercise. We are looking for the field. How A is found. You are A, the cross sectional is given, of course. the cross-sectional area is 20 centimeters square. Okay, according to Faraday's law, the maximum flux can be found from the expression of the induced voltage. Phi max equals to V over 0.44 times F times N. So, and it's equal to 0.202253. Okay, 53 Weber. Now, from phi we found B. Of course, phi here it's maximum, so B, of course, it should be maximum. B equals to phi over A, and it's equal to 0.002253 over 20 times 10 to the power minus 4, which is centimeters square, and it's equal to 1.1265 Tesla. So this is the expression of B max. This is B max. How we can find B? Directly, if B max is 1.1265 Tesla, B is alternating, is 1.1265 sine omega t. That's all. And omega, we have the frequency F is 60, omega is 2 pi F. So this is the expression of B. Okay, so we found firstly phi max from the expression of the voltage, then we found B max from the expression of phi, then from B max we deduce B, which is B max times sine omega t. The second question is obtain the expression of the current in the coil. So how we can find the current? The current can be found from Ampere's law. Okay, the current of always the current is related to H. Okay, so we know that HL equals to NI. Always the current is related to the intensity H. So since we have the density, we can calculate the intensity. So H max equals to B max over mu 0 mu R, because B equals to mu times H. So H is B over mu. Mu 0 is constant and mu R is given. So H max equals to B max over mu 0 times mu R, and it's equal to 358 ampere-turn per meter. And the current, maximum current, because we are working only with maximum here, no problem. So the maximum current, according to Ampere's law, is HL over N. Okay, HL over N. L is the path, the length of the core, the mean length of the core, or the path, which 100 centimeter. So HL is 358 times 100 times 10 to the power minus 2 over N, which is the number of turns, which is, this one is the maximum current because we are using maximum intensity. So the current can be deduced in similar way. So the current, for example, ERMS, we can directly divide this over square root of 2 to find the RMS current. Okay, this one, this is the example. I hope it's clear. As I told you before, here in the magnetic circuit, we have a lot of expressions, but we have a direct application. Okay, we have a lot of expression, but we have a direct application. Inshallah, at the end, I will try and review the all expressions that's mentioned in this chapter. All the expressions starting from the first one, which we have seen, Ampere's law, until the last expression in this chapter. Okay, like that, in order to clarify things. Let's continue. What time? I know there is a football game at 8. Let's try to finish those parts quickly. The first case, we said we can, if you remember, in the first session, I told you, if we want to generate voltage, we can either move the conductor or move the field that the part that produce the field. So the second case, the first case, we are generating voltage according to time varying flux. So this case can be used for AC machines. For AC machines, we have time varying flux. So in case if we have a DC machine, for example, and we want to generate voltage, induced voltage on a conductor, on a moving conductor. Okay, so the first case, the conductor is not moving. Only the flux is time variated flux. Okay, the first case, the flux is variable. It's AC, it's alternative. The second case, we don't care if the flux is variable or constant, but here the conductor is moving. Okay, if a conductor moves within a magnetic field, we don't care if the magnetic field is AC or DC. Okay, the voltage is induced. The voltage induced EMF in the wire is given by this expression. EMF is V, which is the velocity of the wire, cross product the magnetic field density. And we have seen this in our first session, how we can generate an AC waveform. Of course, the cross product, E equals to V times B times the sine theta, which is the angle between those vectors, times L. And if we consider that those are perpendicular, the sine of theta becomes 1, and the final expression is E equals to V times B times L. So I should repeat, to make a difference between the first and the second case. The first case, we said induced voltage using a time varying flux. So in the first case, we didn't mention that the conductor is moving or it's constant. Only the flux is variable. It's alternating flux. So according to Faraday's law, the derivative of the flux equals N times the derivative of the flux. It will give a voltage. In the second case, we have a moving conductor. In this case, we don't care if the magnetic field is AC or DC. We have a moving conductor. So this one is also Faraday's law. Okay, those laws are for Faraday's. Okay. In this case, the induced EMF is equal to the cross product V, which is the velocity of the conductor. B is the flux across the B, which is the flux density times L. So we can find the first expression in AC machines, and we can find the second expression in DC machines. Okay, to be specific, in AC generators and in DC generators. Okay, because in the generator, we excite the machine. Firstly, we excite the machine to generate flux. Then we move the rotor, move with an external force, of course. We move in order to get a voltage. So those are the two cases how we can get an induced voltage, according to time varying flux or according to a moving conductor. The point number 3, it's vice versa of the second case. Here, an induced force. So this expression for motors, not for generators. The last expression is for motors. The induced force is the cross product, the current L cross B, and of course it's cross product B ILB sine theta. Of course, if theta is 90 degrees, so F is equals to ILB. So this is the induced. This is the induced force. So if we have a conductor within a magnetic field, within the magnetic field, a force will get induced in this conductor. Okay, it's a fixed conductor. Okay, at the beginning it was fixed. If this conductor, if a magnetic field cross this conductor, okay. In this case, I will check. Okay, I will check. Okay, so okay, so normally it's a mistake. I will check it. Okay, FBL. Yes, what? It should I cross B multiplied by L. Normally, I will check it, no problem. Okay, معلش. I will check it. So let's repeat. In this case, case number 3, if we have a conductor within a magnetic field, if we have a conductor within a magnetic field and the current is flowing through this conductor, we should have a current. If we have a conductor within a magnetic field and the current flowing through this conductor, a force will be induced in this conductor. Okay, so this is the principle of the motor. The previous case, if we have a conductor within a magnetic field and this conductor is moving, a voltage will be generated in this conductor. So this for DC generator, generally used for DC generator, and this one for DC motor. And the first one is for AC machines in general. Okay, so let's repeat those quickly, those 3 points quickly, and this presentation. Okay, I think we don't have only 5 minutes to end the presentation. Okay. The last element in this presentation is the induced force and voltage. So we can induce voltage in the magnetic circuit with 2 ways. The first case, when we have a time-changing field or time-changing flux according to Faraday's law, the induced EMF is N times the derivative of the flux. We said this expression is valuable with AC in case of AC flux or AC power supply. And this voltage, the last expression, is equal to 4.44 times N times phi max times F. This is the induced voltage in case of time changing flux. The second case is induced voltage in a conductor moving in a magnetic field. So if we have a conductor within a magnetic field and this conductor is moving, a voltage and EMF will get produced or get generated in this conductor, and we use this expression generally. يعني هذه principle of operation of DC generator. Okay, so we didn't specify that the magnetic field is changing or not, but let's consider it constant. So this expression is this is the main expression or principle of operation of the DC generator. The third case, we are talking about the force, not the voltage. If we have a conductor within a magnetic field and the current flowing through this conductor, so this is the difference here. Previously, we don't have current. The conductor is moving, but in this case, we have current. So in this case, when we have a magnetic field and the current carrying conductor, a force will get generated in this conductor. And we can determine the direction of the force and using, of course, the right hand rule. Delete button. Clear. Okay, thank you. Clear all drawing. Okay, thank you. I didn't know this. Okay, so the direction of the force is given by the right hand rule shown in the figure number 10. You can notice that this right hand rule different from the previous. The hand was closed We have only the thumb and the fingers. But here we do this position. Okay. The direction of the force is given by the right hand rule. If the index finger of the right hand points the direction of the vector L, so here L is the one who is taken as a vector, not the current. Okay. So the current here, the conductor, the length of the conductor, which is taken as a vector, and the middle finger point to the direction of the flux density. Then the thumb point to the direction of a resulting force. So this is the right hand rule in case when we want to determine the direction of the force. So here in this hand we open 3 fingers, not like the previous case. The 4 fingers are closed and we have only the thumb. In this case we open 3 fingers. The index points the direction of L, which is L, which is the length, the direction. Here the direction of L, it's the same as the direction of the current, because the current is flowing through this conductor. And B, the middle finger, the points the direction of the B. So the thumb will point to the direction of the force. And this is the last point in this chapter.